Hi everyone. Thank you for joining us. This is a virtual meetup for Data Council NYC. We host those virtual events like once a month for topics around like data engineering and data science. Today we have two talks. The first one is around creating spatial data pipelines, and the second one is about deriving neighborhood and business insights from phone location data. Throughout the talk, if you have any questions, feel free to put in the chat. Our speakers will look through those questions and answer them as the talk goes on. Without further ado from me, let's welcome our first speaker, Matt.
Hey everyone, great to meet you, and yeah, thanks for having me tonight. My name is Matt Forrest, and I am part of Cardo. We're a spatial platform, and today we're talking a little bit about our data observatory, which is what we started out to be a spatial data marketplace, and kind of some of the things we learned from developing and building that. So I'll go ahead and start. Like I said, Cardo, if you haven't heard of us, we're a geospatial platform that allows you to leverage your spatial data along with other spatial data, and you can use that to develop different analyses and solutions. So with that, the core pieces of our platform are kind of fall into 5 different parts. The first is bringing in data. Under the hood, we're a Postgres, PostGIS database. We contribute quite a bit to the PostGIS project, so we work a lot with that. We have many different methods to work with spatial data. The key piece we'll be talking about here is the data enrichment, which is our data observatory that allows you to enrich your spatial data with other data sets that are in the data observatory. The next is analysis. We have a package called Cardo Frames, which allows you to bring map and spatial data into your Jupyter notebooks. And then solutions and visualization, we have front-end toolkits, develop web applications, and build map tiling services. And then finally, APIs allow you to integrate that data out. So like I said, we'll be focusing on that data enrichment piece today. So we started out developing the data observatory because many of our users and customers really had a need to access and enrich their data with mainly demographic metrics, and that's what we started with first. So that's, if you think of demographics, that's primarily census data, things about population, where people live, and stuff like that. And that's really where we started out, is sort of looking at how we can create a tool for people to use that data and use it faster and more effectively without having to onboard that data yourselves. And if you've ever worked with census data, it can be pretty tricky because it's split into multiple pieces. So you have census geometries, things like the lowest unit being a census block. If I'm in New York City, so one single block is usually a census block that goes up to block groups and tracts. It goes even higher to counties and states and things like that. And then you have measures from different components, such as household income, and then there's age bands, household income, population. So it gets to be these complicated pieces, and the data is sort of split and parsed out in different ways. And then there's the issue of the census vintages, which go back for this 10-year census every 10 years, but there's also the American Community Survey, which gives you 5-year sort of rolling updated surveys. They actually send people out and survey the population to give you more accurate metrics. So you have all these different complicated features, and we said, well, we think we can make that easier by hosting that ourselves and giving you a set of functions to sort of enrich with that. So to go back, we have to go back to May 2016. And that is when we launched the Data Observatory officially. And the original Data Observatory, like we said, was just really focused on census data. We started with the US Census, we expanded to Canada, Mexico, and a few other countries. Frankly, the toughest part here is that to get global census data coverage, it can be quite tricky. From the U.S. makes their data quite accessible, as well as many other countries, but sometimes it's hard to actually get that data and have it update on a regular sort of frequent basis. So, like we said, we started with the U.S. Census data right around 2016, and it looked like this. So this is the old version of Cardo. This is called our editor. And we allowed some simple SQL functions to actually select and grab different boundaries. And this is the actual function to go ahead and grab a boundary. So you just basically, select, your geometries and create a table, and then you would insert the geometries that you want into that. So that's how it sort of started. We have our census block groups and things like that. So That's the first piece here. So Data Observatory V1, that integrated data from publicly available sources, things like the US Census, American Community Survey, Canadian Census, so on and so forth. It really only included three things in measures, which would be things like the median income, time frames, and then geometries, which is the actual geography. So that's the first piece there. It only included polygon data, and we can do area-weighted interpolation on that using PostGIS. And what I mean by that is, so if we have maybe a 5-mile radius, a certain number of block groups will fall within 100% of that. And if we're counting the sum of total population, we can count all of those values. But some block groups may fall half in, half out, given the spatial overlap of the boundary plus the radius. We can actually calculate the difference between that, and then calculate the overlap. So that's what I mean by area-weighted interpolation. But it was limited to polygon data. It had limited discovery functions, so it was hard to figure out what data you could use or what might be available at different locations. That was another tricky part, because you may not know what data you want or need at any given time. And then it all ran on a set of functions on our PostGIS database, and it called to a central database within the one of our Carto accounts where all that data was stored. So these are some of the key components of it and some of the key limitations. So what it looks like ultimately to actually get a measure of this, you would have a table. You would set a column that you so choose, like total population. You could call this simple function observatory get US Census measure, pass in your geometry value, and that geometry could be anything: a custom polygon, a radius, a point, whatever. And then you had some specific names, and you would have to go through the documentation and kind of scan and figure out what you would want. And these are all based off of things within the census. So total population is pretty straightforward, but workers over the age of 16, you kind of have to know what you're looking for there. So like I said, discovery was very difficult. How do you help people find the data that they ultimately want to use? So going back, what worked well, enriching your own polygons, it worked really, really well. We could actually pull in your own data, enrich it with the census, and do it all on the PostGIS database, which was really great. You could retrieve census geometries like we showed earlier, and then you could actually cherry pick the measures you want to add for that geometry. So if I was working with census tracts, I could say, I just want these things from the population segments, these from employment statistics, and these from income. So that was quite easy. And it's actually very easy to move between census vintages, right? What didn't work well was enriching lots of features. So if you scaled up and had, lots and lots of locations or geometries or things like that, it started to get quite complicated. The fastest way to do this was actually using some of the JSON functionality within SQL, but it was actually hard for a lot of folks to grasp, and we'll actually break down a query of what that looked like originally. And then keeping track of all these random measure IDs and time frames in a long JSON object was really, really tough. So it just got kind of cumbersome, especially when you're writing queries and you kind of maybe have to keep them in a notepad and all these different things. And the documentation was a little bit dense and it was hard to navigate. So these were some of the things that we kind of found the first time around. Okay, well, it worked, it was fast, it was on a database, but it didn't scale, and we needed better ways to learn and discover the data. So this is an example of what our docs look like the first time around. You could actually go in and look at these measures, and you had to find this little code here, us.census.acs, and this B01003001 is actually the code for total population. So you had to keep track of all these codes and all these time frame measurements, and it was just cumbersome to say the least. And then to actually grab geometries, this was actually the fastest way to do this, was do it with some of these, nested queries and things like this, and then you could, extrapolate the data out using some of the JSON syntax, and it just was cumbersome. Like I said, was even more cumbersome was a query like this, and this is grabbing, I think, 7 or maybe like 10 measures here, keeping them in this JSON, and then inserting them into your new data table here. So this is actually the functionally the fastest way to do that. And so what it looked like is you had to keep track of each measure, determine if it was normalized or pre-normalized, or if it was divided by area, so you can get total population by area. What's the geometry that you wanted to use? What's the time span? Did you want to denominate the data, meaning do you want total male population divided by total population? It just got really cumbersome, and then you had to run a fairly complex query like this to actually get that data updated. So this became, while it was fast, and if you knew what you were doing, you could definitely make it work. It just got really tricky over time to make this really impactful and useful for our customers. So that's where we got into designing the Data Observatory 2.0. And when I was making this deck, I was looking for an original whiteboard where we drew a lot of this stuff up, but I wasn't able to find that. But we ultimately set out with a vision of creating a central data marketplace. And marketplace is key here, with powerful discovery and enrichment capabilities. So the key gaps that we identified is first, you need to cover all geometry types, points of interest, lines, things like roads, and ultimately polygons, which we already covered before. And then enrichment at scale. So we wanted to have it enrich maybe even hundreds or thousands of features wide, and lots of data long. So you could enrich, many polygons and do that quite quickly. We need the ability to add in commercial providers. So there was lots of valuable data, and we wanted to actually have them be a part of our database, our data marketplace as well. Discover data sets and analyze them to actually use and work with them prior to purchase, and use the data in its raw format to actually perform that enrichment. So you want to actually do the enrichment, but actually if you want the census tracks with the data tied to it, you can do that as well. So some quick unique things about spatial data. There's multiple geometry types, like we covered, point lines and polygons. Multiple geographic scales for a single data provider. Like I said, the census provides census blocks, block group tracks, so on and so forth. Varying time ranges. Some have monthly updates. Some have rolling 5-year updates, from the ACS. So there's another complicating factor there. There's varying scales. So there's, enriching data, you could have a very complex geometry, or you could have a large number of points. So it's different ways of working with, in terms of the complexity of the data could be in many different forms. So when we started actually building this out, the first piece was focusing on discovery and enrichment. We designed a new schema to cover the different needs, and we really wanted to enable people to learn about the data in a very clean way. And we wanted to develop an API for them to do that, and we did that within our product CartoFrame, so it's all accessible via Python and a Jupyter notebook. And then we created a database schema to connect all these different components together. And what the components ultimately looked like are these. So the first is a catalog, is actually initiate the catalog so you can start seeing the data. And then you look at categories. So the data categories that we have might be demographics, it might be financial data, it might be human mobility data, which we're going to learn about in the next talk. So you can actually look at the categories of data you want to use. And then within that, there's different providers. Some are open source and freely available. Some are commercial. So there's a distinction between that to see which providers there are and which they have. The next is, where is the data? Which country is it available for? If I'm doing analysis in the US, that's great. But if I want to look at just data in Norway or in India, I can certainly do that as well and figure out what's data available by country. The next is the geographies we mentioned. What's the data available? Is that a point? Is it a line? Is it a polygon? What type of polygon is it? All these different things to sort of associate with the geographies. And finally, we get into the final data set, which is the actual thing you work with most, and then the variables within the data set. So this is all these components kind of compiled here, and this is sort of what we landed on. There's a database schema that maps to the two most important things, which are the data sets and the geographies, and then all these other pieces map to that. They have, each geography is associated with a provider, as well as the data set is associated with a provider, and so on and so forth. But the majority of the data is stored in these two pieces, the geographies, the data sets, and everything else kind of maps to that. So how do you actually do this? This would actually be something that you could do in a notebook. And I can definitely, this is all, you can check out our docs on our website. This covers that too. But the first piece is you actually initiate the catalog. You decide what country you want to look at, and then you pick your categories. So what we see here is we can see here's our different categories. We're able to quickly add a new category, so it's flexible. So we added COVID-19 data, financial, housing, human mobility, demographics, and that allows you to see what categories are available. So then once you pick your category, you can say, what are my providers? You can see here's some of the different providers. This would be the ACS. These are some of the commercial providers. You can actually see who's what there. And then once you actually pick a provider, you can see, okay, here's the data sets that are available from that specific provider, and just expose that as a data frame. So there's actually a lot more here. I just clipped out this image really quickly to highlight it, but you have some identifying information, some names, the category of the data, the country, the data source, provider, geography name, so it's at the country level, and then what's the geography description, what's this temporal aggregation. So there's a lot more there in terms of descriptions, but it's all available via data frame, so you can actually easily scan through that and see which data you want to use. And then you can quickly say, once I've selected a data set I'm interested in, you can get the coverage of that data set to see it's a nationwide coverage. Some data will show up in different levels. And this is, we'll talk a little bit more about the visualization of the data in a minute too. And then actually describe it. So you can say, okay, for that data set, can you, just as you would in Pandas, a quick describe function to say, okay, what's the data look like, in the same way there, without actually having to license the data before that. So you can actually just subscribe to the data. You have to subscribe to the data set and the geography. You can view your subscriptions. And then this is where all the fun stuff happens, which is the enrichment. So you import your enrichment. You are creating a new data frame here, and you enrich your polygon. So you pass in a data frame here. It has to be a geodata frame. So you create that with the geometry object. And then you pass in an array of variables that you want to enrich with. And that can be, we can enrich in like up to 50 at a time, but then you can create loops through that to make it much faster and loop moreover, and then you ultimately get to enrich your polygon here with the data that you've so chosen to do. And I think this is a number of cars per household or something like that as a specific feature here. So this is just showing one, but you can do many, many more, which is the great part. So the key problems here we kind of worked to solve were the discovery, the enrichment, making it very, very fast. Now, the cool part about all this is we basically found that we needed a different database. Really turned out to be a data warehouse to do all of this, and we ultimately run that off of BigQuery. BigQuery provides a really great geospatial functionality for us to use that. The data warehousing, since we're housing a lot of data that may or may not be used at different times, so it allows us to keep a lot of data on storage, and then once used, and we can use that and just compute with that data, and then the distributed computing to do very fast enrichment. So if we wanted to enrich much faster than we could on just a standard PostGIS database, this allowed us to do that really at scale. So what we're working on next is kind of bringing all this into a more usable catalog for those who don't use Python or Jupyter notebooks. So the APIs there, it's just now exposing that back end into a front end to do simple discovery through the interface like this. And then visualization we'll get to in a minute, which is this piece here. But actually, you can kind of click through, search your data sets, see what's available. You can see if you're subscribed to the data set, some of the variables, quickly visualize it, things like that. And then ultimately view your subscriptions and work with the data that way, or actually request some of the data and pull that out. The next cool part I think that's here is actually, okay, now we want to, and if you remember sort of how our platform works, so get to a visualization component within some of our front-end toolkits. And what we actually found the need was, okay, all of our data is on BigQuery. We need to visualize it, and there's actually we built a great tool to kind of visualize some data on BigQuery. So you can read a little bit about it on our blog, but this is actually the BigQuery tiler, which is pulling, this is like 11 million points. This tile set was created within, I think, 56 seconds. So it's actually pulling all this point data where we can actually leave the data on BigQuery, quickly create a map tile set that we could add to any base map and visualize that here and do that very, very quickly. So this is something new that we're working on because we found that people want to use and enrich the data, they want to see it as well. So this is how we're sort of working on and building that. So this is something cool. This is in beta right now if you're interested in checking that out. But yeah, that's kind of what we've been doing. So I would say with all of this, in terms of the key lessons, I think one is that spatial data is pretty unique and people want to use it different ways. Some people are really focused in on visualization. Some are really focused in on doing the enrichment and creating spatial features at scale. And then the key component was working on discovery. How do people learn about and find these data sets? So all that said, what we found was that finding a really good spatial database to do this on is critical. Finding the correct schema and then exposing it and making the marketplace flexible so we can quickly add in new data sets and change them with all the different variables we had to work with was really important. So that's sort of the talk for today, and then we can take questions from there. So I see one for Lexi here. I realize I'm talking with like a shadow half in my face this whole time, but you mentioned that U.S. Census data is especially good. Have you been able to find comparably good data for Europe? And what about Asia and LATAM? So we do have there's one data provider actually called Michael Bauer International, and they actually provide a lot of the global demographics for many different use cases and companies. So it's actually, they provide really solid demographic data with global coverage. And what's cool is they keep the measure levels the same. So if you want to look at populations, I think in like 10-year bucket or something like that. If you want to look at that in Poland, you can look at the same measure in Colombia or in the U.S. So they have great data sources there. So that's actually one that partner that we work with. It's quite popular in the geospatial community. They've been doing this for years. A lot of the census, they make their data available, so you can actually pull some of that data, but it's kind of tricky on how you find that and where it is. And is there anything about the 2020 census versus 2020 or 2010 that you're excited about? I think it's more everyone's kind of watching it with. They're curious about it just because of the pandemic, figuring out how people will respond to it, what they're going to collect, and some basically how they're going to use that data, because they're still sending people out into the field to collect the census responses. Is that going to be delayed? There's just a lot of questions around when is more than anything. So I think that's the biggest component. There's not a lot that changes from the two different censuses, apart from drawing and changing the census blocks, which of course affect everything that scales up from that. So the census blocks, block groups, so on and so forth. So I think that's really the thing that everyone's watching, is how is COVID going to impact what comes back from the census, and that's kind of a big TBD right now. So we're all kind of watching that.
There are also two other questions in the comment.
Okay. Can Cardo customers analyze spatial data that they may have in their own BigQuery data sets? So yeah, Cardo has a direct BigQuery connection. So if you actually have data that's living in BigQuery, you can take that, create either a view or just a standard query that you're using in BigQuery, and directly connect that into Cardo to quickly pull that in and analyze it there. So that's basically what you can do, and you connect it that way. And the same thing if you want to use the BigQuery tiler and you're already a BigQuery customer, it's quite easy to do that. So we work really well with BigQuery, like we said, the geospatial functions plus the data warehousing and distributed computing just made perfect sense for what we were trying to do. So it's a really, really good way to use that. And then the next question, calculating the weighted average of a grid variable over a shape. So it's actually just an open source solution. It's actually using it just uses originally PostGIS functions, but then comparable geospatial functions in BigQuery. Effectively, what you want to do is get the percentage overlap of the polygon. So imagine I have my radius and I have a polygon that falls half in, half out. I'm going to calculate the area overlap of that, know that's 50%, and then count 50% of the variable. Now we're finding some new ways to do that a little bit more intelligently, especially with things like population. There's some really good open sets that we have in the data observatory for population grids that allow you to see really granular views of population data. So you can say, okay, since we know population isn't likely distributed equally within the polygon, can we weight that some sort of way? So that's something we're actually working on to say, not just the pure area component, but actually do the overlap over there. But it's a simple PostGIS function in terms of calculating the percentage overlap of the area. Use the ST area of ST intersection, which gives you the area overlap, and then you take the total component of that variable, so the value, and then do the math there. So if you want to, if you have any questions on that, you can definitely email me. It's just Matt@Cardo or LinkedIn or something like that too. So. And then I see one more. Speaking of the pandemic, are there one or two especially interesting geospatial analyses we've seen around COVID? In the early days, it wasn't so much analysis right away. It was really just response. So one thing we partnered with, several different, sort of areas in Spain. We're a Spanish and U.S. company to actually create an app for people to self-diagnose, and then they were able to actually pull in areas to see where people who have likely reported symptoms are sort of clustered, and you can actually deploy different testing units and things like that. So when things were really rough, that was one that was very just quick response, figure out something like that. And then I think as it's changed now, it's looking at a lot of the mobility data to see where people started from, where they moved to, how they're traveling and things like that have been really, really interesting. So that's kind of, we're going to talk about mobility data next, which is really great, but that's definitely one that I've seen that's been very, very interesting. Spatial epidemiology is a very interesting and complex field, and I feel like there's going to be a lot that comes out of that, especially as this kind of, we learn more and more, but just the response and from many different areas, from data providers to people working with geospatial data, has just been really, it's been a strong response. So there's a lot with that. And then one more question, we mentioned mobility data. How are you working with people movement data? So we work within a lot of use cases. It could be anything from retail analytics to derive trade areas for people who have shopped in a store, all the way up to things like COVID. We actually worked with the city of New York to actually understand, the visit change to different, sort of key locations like pharmacies or grocery stores, to see, well, visits overall dropped, but the length of stay or the new visits in the trade areas sort of have gone up. So, while like a Trader Joe's that's down the street from me actually saw less visits, the demand was much higher. So it's kind of understanding, okay, over the city, which areas or which stores have more people visiting them, how is it changing, what's happening there, and things like that. So that was a really interesting way to use that data. But there's a lot of use cases for human mobility data. It's a really very interesting data set. So. Great.
Yeah, I think that's all the questions we have. Thank you so much, Matt, for the talk. Let's see. Our next speaker is Dr. Song Gao. He's going to talk about deriving neighborhood and business insights from phone location data.
Okay, thanks for the invitation. So I'm going to share my screen now. Can you see my screen now? Okay. So today I'm going to talk about the data and also the recent work we analyzed about neighborhoods and business insights using the mobile phone location data. So our topic is more aligned with place-based social sensing through location-based data. And in our lab, traditionally we utilize surveys, GPS trajectories, and also collaborating with some phone call companies using the call detail records, CDRs, or using social media, or until recently using the location-based apps, and to understand human mobilities and movements, and then their social tiles or social network, and also how they perceive or what are their emotion sentiments about what's going on in the world and specific different places. And as a geographer, and we utilize such individual level human behavior data to understand our geographic environment. And today, in collaboration with SafeGraph, we are specifically talking about how to utilize such a different sourcing data to understand the places in the world. SafeGraph is a data provider and provide 4 types of data products, including core places and geometry, which such as a building footprint. You can understand, for instance, a Starbucks in a strip mall, and or for those specific business. And place patterns, later I will introduce you how to use that. Actually, Matt also mentioned that, how to understand the dynamic foot traffic using the place patterns. And lastly is the neighborhood patterns. So we actually utilize in our research. So this is a overview about the spatial footprint of those points of interest get from SafeGraph, and this is just a visualization, give you a sense about the spatial coverage of those POI data. The more lighter area, most of you are in New York, and it's a more urbanized area and more dense business distribution. And one of the research we did is actually utilizing the neighborhood data and to understand the human mobility flows. Specifically, we utilize the origin to destinations OD flows and to understand how people move around city. And for us, we are specifically interested in different racial and ethnicity groups, how they spatially interact at the different neighborhoods, and utilizing such a socioeconomic data with the mobility data can help us understand, such as isolated communities, they may have less frequent interaction to maybe to higher income communities, and then such analysis can support like a disadvantage of community detection, racial justice, and city planning. So this is one way to utilize the neighborhood pattern in our research. Also, in our recent work, our lab collaborated with MIT Sensible City Lab, and we utilized multi-source big geodata and with machine learning, trying to understand the house price appreciation rate. So a lot of study has talked about the house price modeling. However, there are a few work talk about the price appreciation about, for example, whether increasing space or decreasing space. So this is our research focused on in this particular work. And this is workflow, and there are 4 components in the data collection. On one hand, we collected the traditional house information such as house size, number of bedroom, and other structure information. But also from those real estate website, we can also collect house photos to understand the appearance of the house. And another component is understanding the locational amenities. So this part, we can utilize a lot of point of interest POI data, and also integrating the transportation accessibility and the foot traffic data, and also social demographic data. So after we have data in the second stage, we use the feature engineering approach to extract those high dimensional features from those multiple data sources, and then train different models at different geospatial scales, and also do the final step doing the prediction and also the mapping and analysis to have a better understand the house price appreciation. And give you more details, in this particular study, we use the Boston metropolitan area as a study area, and we use the information in both year 2019 and year 2014, and to calculate the price appreciation rate. And here are those spatial distribution of the houses, and also their sensor block groups boundary, and also collected the Google Street Views and the house photos inside from those real estate websites, and to provide like a human lens of the view about the houses. And to understand the built environment, specifically in the locational amenities, we take the previously mentioned the SafeGraph POI database, and use a North American information commercial system code to integrate different types of categories such as grocery shops, schools, universities, hospitals, natural parks, and so on, and to understand the convenience of the neighborhood. And for the environmental perception, we specifically utilize Google Maps street view images and train deep learning models, and to understand human perceptions For instance, this is actually one of the early work done by the MIT lab. They there is an open data set called a place pass, and it asks people how they think based on the street view images, which places look safer, look more lively, look more boring, or depressing, or beautiful. So based on those human label data, you can train the deep learning models and to understand the human perception about the neighborhoods. So we also utilize, this label data and to train our model, and we use the ResNet and to get different perception scores. And the third type is a human mobility, and we utilize two types. The first one is a safe graph, foot traffic. The second, we also utilize the Uber movement data to understand the accessibility from neighborhoods, to move around the city, how they can reachable from the transportation. And lastly, the socioeconomic attributes such as median house income, the racial compensation in this neighborhood. And this is just a spatial view about all those different data sets we have. And first of all, we calculated the house appreciation rate between the 2 years, and this is log of the house price distribution in Boston area, and this is raw house price, and this is a number of visitors derived from the safe graph data, and this is accessibility from the Uber movements, and lastly, the population distribution. And we build different models in the trying to understand what kind of attributes actually can help model the house price appreciation better. And we try the baseline, which is based on the traditional hedonic modeling, which only considers the house information and then the location amenities. And then we add those different attributes we think might help each time, respectively. And then we also build the model based on all the data sources. And we try just the two basic models, multilinear regression and then the gradient boosting machine. And in all cases, the gradient boosting machines perform better than the multilinear regression. And also, more importantly, is that those new additional data sets, which are not widely used in traditional house price modeling, such as street view images or mobilities, actually can improve the accuracy, across those machine learning models. And one interesting finding actually was that originally I thought actually maybe large house, higher house price may lead a higher price appreciation, but based on big data, actually a lower house price and smaller house areas may lead to a higher price appreciation rate. So because we are talking about the ratio or portion here, so that might be different from the absolute differences. And to understand the geospatial pattern, we also utilize geographically weighted regression to do the analysis to understand the spatial heterogeneity. And here, the different maps actually show such a spatial heterogeneous pattern. For instance, based on the GWR, we can find out even for the performance, if we look at the R-square, the good news of fate, they actually may also have a different performance in different area within the Boston area. So similarly, the different variables such as distance to hospitals or distance to metros, they also play a different role, in different parts of the Boston area. So some of the short summary about this particular case study is that, first of all, taking visual features extracted from street view images and house photos using deep learning, and maybe can take as proxy for the built environment and human perception. And second, taking safe graph foot traffic data and the Uber movements, we can measure the human mobility patterns and further fit into the machine learning models. And last but not least, it's actually important to consider the spatial heterogeneity in geospatial modeling. So this is the first case study. Then I will talk the second, also the last case study, is about the location business intelligence, still using the location big data. Here we focus on the business analysis. Specifically, we talk about trade area analysis. So the idea is to estimate the region that containing the potential customers for a store, with products or services. And to build this model, we should consider on one hand the attractiveness. So what kind of the merchandise offerings in a store, and then the second thing is about the cost, like travel cost, either travel time or travel distance. So this is two types of factors, and they might have other such as seasonal variation, weather, or processing power. But yeah, it's more challenging to model. So we only consider two in the simplistic model. And in terms of data sources, different business use different sources such as membership surveys, the sales, such as also some of the sale report or the transaction data with zip code to link to geolocation, or the foot traffic tracing. And there is one classic model in the location business modeling, so that they call the half model. So the half model is like a gravity style of modeling. So you have attraction, you also have the reverse to the distance, and in this case, we can build the for the specific store where the customer come from, especially the probabilities, and this is the model. So because of time, I will not go into much details, but here you can understand that basic two things we need to consider: the attraction and then the distance or travel time. One of the limitation of the traditional model is that they didn't consider temporal variability. So here we show that this is a 5-store in Los Angeles and or Whole Foods, and the color actually matched the red panel about their actual foot traffic information and hourly. And this is you can see that actually even for the same brand, the Whole Foods, they also have different temporal visit probability. So this inspires us to further modify, the model. So the research question for us is whether they improve the model or not using the new model over time, and how the geography, socioeconomic factors can help determine the customer choice of particular store visits. And first of all, we modify the traditional half model by considering the temporal information. This is a specific formula, and we actually build two versions that just different formats. But the key idea is to incorporation of the temporal visit probability into the model. So in the experiments, we take the SafeGraph place visit data, and we try focus on two types of POIs: the supermarkets, grocery stores, and then the department stores. We conducted experiments in the top 10 most populated US cities. And the red figure showing the visits, the the relationship between the visits probability to the distance. So there is a distance decay phenomenon. So as expected, so people for these two types, people are prefer to visit shorter distance stores. And in order to turn the parameters in the model, we use the particle swarm optimization, the PSO optimization methods, and to get the optimal parameters. And we also, open source the code on Jupyter Notebook, and is available on our GitHub, the THAF model. And so this is summary about comparison between our THAF model and the traditional half model. So our model performed better in terms of prediction accuracy, and this is a prediction result between using the actual foot traffic data from SafeGraph and also our modeling aspects, and this is showing the differences. Actually, most of them are the differences are very small. And another reason why using the model rather than observation is that, first of all, the observation is a sampling, so sometimes you may actually not get the whole population sample. Secondly, what if you don't have tracking about a specific store, right? Because we actually know that even within the large POI database, we cannot track every store. So this is why we have to build some model and then to understand the location visit better. So across different cities, the 10 most populated cities in the US, and we observe the travel distance decay, as I mentioned earlier. And however, people in the large metropolitan areas with well-developed transit system are less sensitive to the long distance travel, such as in New York, right? Specifically for most of you, and compare with people in Los Angeles, right? So one is more, relying on the public transit, but another is really more relying on the private vehicle. So it's actually different. So this is why you can find different, distance decay coefficients in the model. And lastly, we built just a very simple multilinear regression model and to understand those socioeconomic factors, some conclusions, and like total visit count, distance, median house income are statistically significant across different brands, and all the race and ethnicity diversity. We use the entropy value, and it's also statistically significant to the Trader Joe's. Um, for the raw stores, actually, all those socioeconomic attributes are statistically significant. So summary, first of all, we found that by incorporation of the temporal information from the foot traffic data, can help improve the predictability of the visit to the stores. Second, we also found the spatial proximity and demographic socioeconomic factors still play important role in the customer choice of particular store visits. So, um, because this talk was introduced by SafeGraph. Um, so SafeGraph is collaborating with multiple organizations, private, public sectors, and is planning to launch the Place Key, and that is a free identifier for physical places. And this is a link. And if you are interested in about the open identifier for the places in the world, so please keep an eye on this. So that's all. Thank you very much.
I think there are two questions in the chat. Actually, three now.
Okay. So the first question is about any functions to ensure privacy in location analysis. Yeah, this is actually an excellent question. And whenever we present a mobile phone location-based study, this is always the top questions because the concerns about the location privacy. So there are two things. First of all, from the safe graph, what we get is only the aggregated and the anonymized data. So there is no way for us to reverse engineering. So this to ensure the privacy. But for other data sets such as the CDRs or like geotagged the social media, we actually take extra steps in our lab to secure the data and to not disclosure the individual information. But most of our research, as you can see, are more geography focused, is a more aggregation based. So yeah, this is a very important question and also concern. The second question is the talk slide. Yes, I think I will share with Alex later on. And the third is what kind of place key will identify. Yeah, so this is still ongoing discussion, but the idea is that the place key will actually because right now I think a lot of commercial business listing are focused on the business places. So I think that the idea of the place key, the big vision, I think definitely to incorporate more diverse and more complete data sets. But yeah, I think this is why people are still discussing, and then any ideas are welcome, and please keep your eye on the website. Are there one or two especially interesting geospatial analysis I see around COVID-19? Yes. So, in fact, sorry, actually, I can share my share my screen for 5 seconds. Yeah. So actually, I do have one slide. Our lab actually did COVID-19 work with the mobility data. What we found interesting is that, first of all, based on our mobility dashboard, we can find that actually, although around mid-April, some of the states still are in the stay-at-home orders. So such as New York and many others. So New York actually doing great based on the mobility tracking. But some of the states, such as in Florida or others, they actually, people are just, I feel people are tired staying at home, and also because the weather become better, and they already going outside. So this is actually can be tracked by the mobility data. So this is the first thing I found very interesting or even shocking to me. So for us, based on culture, we think we actually should follow his order. So the adherence to the mandates is different. So because the second thing is based on the because we are social science researchers, we have to definitely focus more on about the socioeconomic attributes or the social maybe diversity or inequities. So this is why we in our state we found that, for example, in the county of Milwaukee, and definitely like Hispanic or African American hurt harder compared with other race. This is why we think that there might also still be a something that we can observe from such a mobility data, even like the first slide I showed you about the flow in the Milwaukee. So that's something that can help inform the public health. This is the two things we found relevant, interesting to the COVID-19 geospatial analysis. I think there is another question from Jeff. The people movement data, right? Oh, that is relevant to the privacy question. Yeah.
I think that's all the questions we have. Yeah, thanks again, Dr. Song, for the talk.
Thank you.
And this is a wrap for our event for today. Thank you all for joining. If you use the same YouTube link, the whole session is recorded, and we will also share the slides when we get them. Thank you so much.
Thank you.